This is going to be lesson 8-3, direct and limit comparison tests. So far you've seen the geometric series test, the integral test, the p-series test, and the alternating series test. This series test will be different from those in the sense that we need to know the convergence or the divergence of a different series. So the main goal for the direct comparison test, which is frequently harder, is that if we want to prove that a series converges, then we want to find a larger series that also converges. Because if a series that is larger than it converges, then the smaller series must also converge. If we want to prove a series diverges, then we want a smaller series that would also diverge. If the smaller series diverges, then the larger series must also diverge. So one of the hardest parts about using this test is you have to have an idea of whether the series you're starting with converges or diverges. You have to have an idea of whether you want to go under it or below it. One of those two things should be easier. So just to give you a concept of how this is working, let's say in red we have our series. It goes doot, 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 doot. We don't know whether that converges or diverges. It looks like its limit is going towards 0 as we go to infinity, but remember that that is inconclusive. That does not tell us it converges. So, if we could find a green series that was less than it, like let's say green is the sum of 1 over n. That's the harmonic series that diverges by the p-series test. If it was below for every term, we'd sort of know it would stop it from being able to converge because it would be getting too big from the underneath, sort of, and then it would not be able to converge. However, and I wish again we could just delete the green, but the idea is that if we were to run the experiment again, doot, 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 and we had a blue series on top of it that was converging faster, like let's say blue is 1 over n squared, that's a converging series also by the p-series test. And the idea there is that it's squashing that series down, that it's enclosing. So a lower series could keep it from converging, a lower series could force the series to diverge, and the bigger series can force it to converge. Very hard to do this. It's not going to be that used, but it's still important because it'll make some of your problems much, much quicker if you're able to master this. For instance, examples 1, 2, and 3. So like I said, more practically, the hardest thing to do here is to decide what we want to compare it to. Frequently, the technique we will use for the direct comparison test is just get rid of other stuff in the denominator. So here I have this 1 plus in the denominator. So I'm thinking, well, what would happen if I got rid of that? Then we'd be looking at the series 1 over 2 to the n. Now, it's imperative at this point that you understand that this is a geometric series. It inspires being weird. Geometric series with r equal 1/2. Good. If you've said 1/2 or thought 1/2, you are right. So the absolute value of r is less than 1, so converges by GST. Now, we also then need to say, and I know, I don't know if you guys know, but I know 1 plus 2 to the n is always going to result in a smaller fraction than 1 over 2 to the n. Now, why is that? By taking away 1 in the denominator, I've made the denominator smaller, so I've made the fraction bigger overall. Whenever I make the denominator smaller, the fraction is getting bigger, increasing in value. Like, I have a fraction of 1/3. When I subtract 1 from its denominator only, I end up with 1/2, which is a larger number. 0.5 compared to 0.333, whatever. So here, I know that. And this is what I'm saying. So here's the two parts. I was able to easily find a series I could compare it to. Here's the comparison. This guy converges and is bigger. I would need converges and bigger or diverges and smaller. So since this converges and is bigger, our series that we started with, 1 over 1 plus 2 to the n, converges by direct comparison test. So yes, you need to say this, you would need to say this, and you would need to say this. Now, next one. It's really the same trick again. It's the same trick over and over and over again. It's just a matter of what you can or can't do. So what would I compare this one to? If you said or thought the harmonic series, you're just showing off. If you said or thought this guy, you're right. This guy is the harmonic series. This is our harmonic series. This is the harmonic series. The harmonic series is also known as the P series with n equals 1. But I'm going to say this diverges because it's a harmonic series. Because harmonic series. And again, in case you don't remember what harmonic series, P series with P equal 1. It's a very special series. It's a good one to keep in mind. It's what shows you the limit can be going to 0, and yet it could still diverge. This diverges, and its limit is 0. Keep that in mind so you do not make the most glaring mistake of all, which is say converges by the nth term test. Never, ever, ever do that. So here we go. 1 over n minus 2 compared to 1 over n. So is this bigger or smaller than that? So I've added to the denominator now. This denominator is 2 larger than that denominator. So because this denominator is bigger in value, the fraction is smaller. Because this denominator is larger, the fraction overall is smaller. So what we have here is a diverging series that is smaller than our original series. I have a diverging series that is smaller than the original series, so therefore this guy diverges. Oh my gosh. By the direct comparison test. Diverging smaller means the parent series, the original series, diverges. converging bigger, the original series converges by the direct comparison test. All right, this one. So if you're paying attention to the trick we used, if you're paying attention to the trick we used in the last two examples, you would correctly conclude that we're going to try this one. Now, why do we know whether that converges or not? What type of series is that? If you said or thought that this is a P-series test, or a P-series with P equal positive 1/2, not negative 1/2, that's a really big mistake, then we also know that diverges by the P-series test, because P is less than 1. P-series test. All right, now I consider my original series versus the new one. I'm sorry that fraction's so ugly. I'm not going to re-record the whole session just to get that. So, I'm considering these two fractions. So again, I think about, well, what's the denominator here look like compared to the denominator here? This denominator is 1 bigger. A bigger denominator results in a smaller fraction. Now pause. A lot of you are probably already writing down, because frankly, if you're smart enough to jump into BC, you're probably the most likely to have the smart student syndrome, where you think you understand this. A lot of you are like, oh, so it diverges by the direct. No, it doesn't. In this case, this would be a bigger series that diverges. And if we go back here, I need a smaller series that diverges, or a bigger series that converges. I cannot do anything with a bigger series that diverges. So, this is a dead end. And it's a number one trap problem. I am sure many students will fall into this trap on the AP test, because you just think, oh, it had to work. No, it didn't. No, it didn't. So that was a complete dead end. But it's important to see that dead end so you don't just rush off headlong into disaster. So let's try something else. And this is where you have to really get creative. Well, let's look at our good old-fashioned harmonic series. How could you think of this? How would I think of this, Mr. Leven? And I don't know. I frankly don't know. I probably would have done this problem with the limit comparison test, which you'll see in a second. Diverges, harmonic, right? And a moment's thought shows that, as one of my favorite professors would say. 1 over root n plus 1 is bigger than 1 over n. At least when n is bigger than 3. Bigger than 3. Bigger than or equal to 3, I think. And you could just check that, right? Like try 4. Root 4 plus 1. 2 plus 1. 1/3 versus 1/4. N equals 16. Root 16 plus 1. 4 plus 1. 1/5 plus, 1/5 versus 1/16. Okay? This is definitely smaller. Like, okay, try. And I'm thinking this, you wouldn't write it down. Try n equals all the squares you can think of. So that diverges. It's a smaller series. I have diverges and smaller. So this guy diverges by dct. Oh gosh, I didn't write diverges. I'm sorry. So this one's hard. And in general, the direct comparison test is hard. It's easy when we can have good times, when knocking out one piece of the denominator makes everything go away. But we can often have problems where doing that kind of stuff just doesn't work. And in that case, we'll use a limit comparison test, which I've labeled as fun, and that's not a joke. The limit comparison test, you will need to use limits. Surprise, surprise. Who could have predicted that? You need pretty much everything to be positive, and you need L to be finite and positive. Now, what some students do not understand is that means bigger than 0. If I have a limit of 0, this test is not working right. You want to have a limit of 1, a limit of 2, a limit of 3, right? Those are positive numbers. You do not want your limit to be 0. And in case you can't read, what am I doing? I'm taking a limit of an to bn, where an is one series and bn is a different series. So if that limit is finite and positive, then the series either both converge or they both diverge. I don't have to worry about smaller, bigger, whatever. And that's fantastic. So this series test works really well when you're comparing a messy algebraic series. Algebraic, like a polynomial, like I would have talked about in the integration by parts lesson. I'm recording this before I do that, so it's a little confusing to me. So, an algebraic series to an easier p series. And again, that's n to the p, where p is constant, n is changing. To choose the p series, you ignore all but the highest powers of n in the numerator and denominator. This is a lot like just doing limits, finding the horizontal asymptote. Here we go. Oh gosh, it's so hideous. I can't do it. What I'm really thinking when I look at this is, well, knocking out this 4, if you wanted to try the direct comparison test, knocking out this 4 gives me something that is bigger in the denominator, so it's smaller as a fraction, so it does not follow the direct comparison test, right? If I tried the direct comparison test, I'd have something bigger that I'd have something smaller that converges. And again, I don't want smaller converges. I want bigger converges or smaller diverges. What I'm saying is, after this, you might not use the direct comparison test unless you're told. What I would do instead, I look at the top. What's the highest power on top? If you said 1, you're right. I look at the bottom. What's the highest power of n on the bottom? If you said n squared, you are also right. And that's how easy this can be. And I would say, oh, that is a p series with p equals 2, and 2 is bigger than 1, so this converges by the p series test. And what do I want to do? I want to take the limit as n goes to infinity of this complicated fraction, but it's going to get simpler in a second. Actually, I'm going to color code this better for you. See, I picked orange and it won't let me. It doesn't matter which order you divide it. Maybe some of you already wrote down a division in another way. It doesn't matter which order you divide. So I'm doing that limit as n goes to infinity. You have to be strong with your fractions to know why I can write this. I'm going to keep, change, flip, kids. Don't lose your marbles. Now, I'm recording this in the morning. I kind of feel like Rahul's about to walk in. So if I yell at Rahul, don't worry. So keep, change, flip. And you won't use L'Hopital's here. You would just look at this and see, oh, it's just what I've been doing since pre-calculus. What's the coefficient on the top of the highest power? 1. What's the coefficient of the bottom's highest power? 3. Bam, because they match. Oh, goodness. So it's 1/3. 1/3 is some finite, not infinite, and positive. Check. So, since this guy converges, the original series I started with converges by limit comparison test. Hooray! Now, I don't know what I'm going to do. Green, I guess. I don't care. All right, limit comparison test. What am I going to compare it to? Highest power on the top. Highest power on the bottom. Simplify. 1 over n to the 1/2. Good. Yes, it's a slash. I can deal with it. Okay. Why do I want to write it like that? Because then that's a P series with P equal 1/2, which is smaller than 1, so diverges by PST. P series test. P series test diverges if P is smaller than 1, converges if P is bigger than 1. So I want to take this limit, make sure you understand why I'm writing what I'm about to write. Why I'm writing this. I have root n over n plus 7 times n to the 1/2 over 1. But Mr. Leven, you said we divided it. I did divide it. I just kept, changed, and flipped in my head. From this point on, you will be dividing so many fractions that you should just know you can just jump to the step where you're multiplying by the reciprocal. Okay. Notice how I'm writing the limit. Notice how I copy the limit. You want to make sure you do that. They will care. What's root n times n to the 1/2? Hopefully you either realize this is n to the 1/2, and therefore it's n to the 1/2 plus 1/2, or n to the 1. Or you realize that this is root n, and root n times root n is n. And wouldn't you know it, because I did the limit comparison right, because I compared it to the right series, my limit's going to work out to be coefficient on top, coefficient on bottom, 1, which is finite and positive. So this series, an original parent series, diverges. Why does it diverge this time? Think about that. By LCT. It's diverging this time because the comparison series was diverging. That's it. You don't have to worry about being smaller. You don't have to worry about being bigger. It's just great. Right now I kind of felt like it wasn't recording. Please be recording. It's either going to be funny that I'm saying this, or I'm just talking to myself, like I am in class sometimes, and it's going to be really tragic. So if you're laughing at this, at least we're living in the good reality. All right, who do I want to compare this guy to? What's the highest power on the top? If you said n, you are correct. What's the highest power on the bottom? If you said n cubed, you are also correct. What type of series is this? It's definitely a p-series. It's a p-series with p equals 2. 2 is a larger number than 1, so this converges by p-series test. This is why you want to know everything about p-series and everything about geometric series. They're your go-to series. They're the series you need to know whether they converge or diverge instantly. So now I'm taking this limit as n goes to infinity. The original blah, blah, blah. Copy, copy, copy. Yes, you need to write it all out. You at least need to write the limit out. But Mr. Leven, I know where... Yeah, write it out. Just write it out. Keep, change, flip. But bam. There should be no surprise at this point because I'm the one doing it, that it's going to work out nicely. And that's why after this is done, you should maybe try out a few problems. Or I don't know, just watch it again. And again and again. Well, there's so many other things to watch. So many other lessons to watch. I'm not... Like, you should just be watching this all the time now. Put this on. Eat your dinner. Whatever. Alright, so coefficient on top, coefficient on bottom. Now, I don't want you getting sloppy. That limit trick only works for polynomial over polynomial. Don't do it with e and e or something, okay? Be smart. This is what you've been doing. This is a rational function. And with a rational function, it's the ratio of the coefficient on top with the coefficient on bottom if the powers agree. You could really mess this up by making the top too big or making the bottom too small. Oh, or making the bottom too big, and then this won't become a finite and positive number. Boop. So, because the one we compared it to converges, so I really don't want to write it, but look how I'm writing it. The fact that I'm writing it means you would need to write it on a test. Converges by LCT. So now you've seen the basics for the direct comparison test and the limit comparison test. Those are two that are called the comparison tests, plural. I would practice some problems. What you'll see, the next lesson is a little bit harder than this, and also in some ways a little bit easier. But you should make sure you understand this. The limit comparison test is much more flexible and much more easy to use. So if you were going to focus on one test to practice, I would practice the limit comparison test. If you look at assignment 8-3, you will see that some problems ask you to use a direct comparison test. You should master that too, because it's, again, faster. It's faster than doing this, because most of you guys would mess up a limit at some point. I'm going to stop the recording now and pray that it was recording. So I think I stop this first.